Hello, everyone. Today, we'll be starting with differential equations. If you recall, when we started integration, we talked about how to solve a differential equation using analytical approach. Once again, I'm going to start in this lecture with what is the definition of a differential equation, an order of a differential equation, and finding solutions of these differential equations. Now, we're going to be using initial conditions to find particular solutions of this differential equation. And as I said earlier, in section 4.1, we had started with differential equations, but this time we'll be using the same techniques, but the problems will have exponentials and logarithms too. And then finally, I'll be looking at a numerical approach to solve these differential equations. And the numerical approach we're going to be using here is called Euler's method. Okay, let's begin. So what is a differential equation? It is very simple, an equation that involves derivatives or differentials. For example, 3xy prime minus y equals natural log of x plus 1. Or we can have xy prime minus 2y equals x to the power 3 e to the power x. Or we can have a second differential equation, this s double prime of t equals 32. Or we can have a fourth order differential equation. This should be y. This is a fourth order differential equation. Sorry for this little typo. So, or we can write this as dy4. Suppose my independent variable is x minus 16y equals 0. So similarly, we can have s prime of double prime of t. We can write this as, this is dy4. Wrote this wrong. Yeah, so it is the second differential of s with respect to t. So d square s dt square equals 32. Now remember, recall y prime can be written as dy by dx, because here the other variable in the first and the second differential equations is x. So just using that idea, we can write as dy over dx. So this is just a short form of writing a differential dy by dx. Moving further, so we have these four differential equations. We're going to look at the order of these differential equations. Now, the order is determined by the highest order derivative which is present in these differential equations. For example, in 3xy prime minus y equals natural log of x, the highest order of derivative is 1 because it is only y prime. Remember, as I said earlier, y prime is dy over dx. Okay, the same goes for the second equation, xy prime minus 2y. The order is 1. Now let's look at the order for s double prime t. And I just wrote earlier, s double prime t is d2s over dt squared. So the order over here is 2, and the order for the last differential equation here on the slide, y to the 4, this means this is a fourth order derivative. Okay. Now, as I said earlier, we have learned previously the approach to finding solutions of these differential equations in the analytical way. This time, we're also going to be looking in terms of numerical. And there's another third approach, which is called the graphical way of solving these differential equations. Our main focus would be on the analytical and the numerical approach on solving these differential equations. Okay, let's start with analytical solutions. So a function y equals fx is called a solution of the differential equation if the equation is satisfied when y and its derivatives are replaced by fx and its derivatives. Okay, so what you're basically doing is, if I have I want to find that if y is a solution, I'm just going to go and look at the differential equation, substitute the value of y which is given to us, and the corresponding also there's some derivatives. Now, for example, y equals c e to the power negative 2x is a solution of this differential equation, which is given by this y prime plus 2y equals 0. Now, remember here, c is a constant. Now, as we're saying, it is a solution. So that means when I take y and I take its differential and substitute in this equation, say it is equation 1. So I substitute y equals c e to the power negative 2x in this equation 1. The left-hand side should equal the right-hand side. So let's just go ahead. Now we already have y equals c e to the power negative 2x given. The other thing we need over here is just the first differential. So let's go ahead and find y prime. So y prime equals, now c is a constant, we don't do anything. What is it? Differential of e to the power negative 2x? It is simply e to the power negative 2x. But remember, you will have a constant in front of x. So you will take the differential of negative 2x. So what are we going to get? C e to the power negative 2x. And differential of negative 2x is negative 2. So what do we get? Negative 2 times c e to the power negative 2x. Okay, now let's go ahead and substitute it over in equation 1. So we are going to substitute y and y prime in equation 1. Okay, so what is y prime? Negative 2 c e to the power negative 2x plus 2, and what is y? C e to the power negative 2x, c e to the power negative 2x. Now remember, I'm starting from the left-hand side. So clearly these two terms are opposites of each other, so we get 0. So when you substitute on the left-hand side, we get 0, which is the same as the right-hand side. And hence, y equals c e to the power negative 2x is a solution of this differential equation. Now let's look at another example. And it says determine whether y equals natural log of x is a solution to the differential equation given by xy prime minus 2y equals x to the power 3 e to the power x, and our x is positive. Now remember, this is a solution. A natural log functions, x always has to be strictly greater than 0. You cannot have x to be 0. So that's why this is needed over here, this x greater than 0. Okay, so what are we going to do? Now, in this equation, we have y and we have y prime. So let's go ahead, look at this. We are given y, natural log of x. Now y prime, because my x is positive, we don't have to worry, it is 1 over x. You see, this is x is positive, so everything works. Now, what we're going to do is to check whether the left-hand side equals the right-hand side of this differential equation. So let's do substitution. Y and y prime in the above equation. So what do we get? We said x times y prime, which is 1 over x, coming from here, minus 2 times y, which is natural log of x. Now remember, I'm going to start with the left-hand side and see when I solve this left-hand side, do we get anything which is on the right-hand side? Clearly, when we do the solving, what do we get? 1, so x and x cancel out. Okay, so this x and x cancel out. So we have 1 minus 2 natural log of x. This is nowhere equal to the right-hand side, which is given by x cubed e to the power x. This is your right-hand side. So clearly, the left-hand side of this differential equation is not equal to the right-hand side. And hence, y equals natural log of x is not a solution to the differential equation. Okay. Moving on further, let's look at this problem where it says determine whether y squared minus 2 natural log of y equals x squared. So this is the equation. This is the equation which says whether this equation is a solution to the given differential equation given by y prime equals xy divided by y squared minus 1. Okay, now let's look at the equation which is given to us. Clearly, this equation, notice, is an implicit equation. So if I want to find a solution of this implicit equation, if I want to check whether this implicit equation is a solution, and find it the usual way we have been doing, it's not going to be easy because it's very difficult to get y on one side and everything else on the other side. So over here, we're going to take a different approach. Okay, so here, the approach we're going to do is a different approach. Let me write it down. A different approach will be taken. And that approach is that we will do implicit differentiation or I would say we will apply implicit differentiation on this equation y squared minus 2 natural minus 2 natural log of y equals x squared. Okay, so let's start. So y squared minus 2 natural log of y equals x squared. So what do? We are going to, okay, so it changes everything. So let's just keep it. Let's do that, doesn't matter. We were going to take the differential d dx on both the sides, and I need some more space. So let me redo it here. Okay. Equals differential of x squared. Now notice that this equation, which is given on the top, the right-hand side is easy because the independent variable x and the function which is given to us are both having the same variable. So this right-hand side, very simple. Now, let's do a little bit more further work. So that means differential of y squared minus, we're going to take the differential of 2 natural log of y. Okay, notice over here, okay. that the x and the y's are different. Okay, so in that kind of scenario, we do the normal differentials. If you recall back from the integration chapter, we take the differential chapter. What we do is we look at x and y. They're different. We do the normal differential. So we'll write this as 2y, and then we multiply by dy by dx. Negative. Now, once again, y and x are different. So I'll take the 2 outside, and then they take the differential, because remember, 2 I can take outside, it's a constant. Natural log of y equals 2x. So on the next line, I will do my differential on natural log of y. So it's going to be -2. And you're going to have 1 over y. And we're assuming that my y, so here's my assumption, that my y is positive. Okay, otherwise you'll be doing 1 absolute value of y. So I'm making that assumption so that I can easily not worry about the absolute values. Okay, so this is my assumption I'm taking. 1 over y times dy by dx equals 2x. Now notice, 2 is common everywhere. So if I can take the 2 out here, so I can say y dy by dx minus 1 over y dy by dx equals 2x. So I can cancel the 2's on both the sides. What are we left with? We're left with y dy by dx minus 1 over y dy by dx equals x. If you remember, for implicit differentiation, we gather the dy by dx terms together, which is already done here. And now we will combine the elements which are, we'll get the dy by dx and kind of factor in the values. So combine the terms, like terms, minus 1 over y here equals x. Now, remember, we want to get it in this situation, which is given over here. We want y prime equals xy over y squared minus 1. So y minus 1 over y. Okay, I wrote it here. So I want the dy by dx to be on its own and y minus 1 over y to go on the other side. Okay. So what do we get? Dy by dx equals x over y minus 1 over y. We're very close to the answer, but we're not exactly there. So we just do a little bit computation. Now remember, I would like to have one fraction, not a fraction and a fraction inside another denominator. So we're going to make one fraction in the denominator, and we're going to have common terms, which is y, and we can write this as y squared minus 1. And then what we're going to do is, to have nice fraction, we will take the denominator, and when you take it on the top, what's going to happen is we will have x over y, y squared minus 1. So basically you're going to flip, when you take it on the top, this division becomes like a multiplication of y over y squared minus 1. So ultimately, what are we getting? We're getting that dy over dx equals xy over y squared minus 1. And that's exactly what we have over here. Okay. Now, what we have been doing is making sure either equation is a solution or not a solution. So we're basically trying to figure out whether a given equation is a solution. Now, what you're going to do is we will actually find a general solution of this differential equation. And we're going to use integration to do that. So let's look at this equation given to us. Dy by dx equals x e to the power x squared. Okay, we want to find the solution of this differential equation. remember what we said earlier, that the solution of a differential equation is given by y. This is the solution of a differential equation. So ultimately, what I want to do is I want to find y. I want to remove the ddx in front of it. So in order to do that, first I'm going to write it in an equivalent form of this differential equation. So I can write this one as dy equals x e to the power x squared dx. So both these equations are equivalent form of each other. So this is an equivalent, a proper way we say this is a differential equation, and this is the equivalent differential form, whatever you want to say it. Now, the way, if you remember that to get rid of this d, what do? We take the integral on both the sides. So now we will integrate the above equation. What this basically means, integral of dy equals integral of x e to the power x squared dx. Now, the d and the integral, they're basically opposites of each other. So we can basically cancel this one out, and we can say this is y. Now, on the right-hand side, now to find the integral of this function, we're going to use u substitution. We say let x squared equals 2 u. So now we differentiate, we get 2x dx equals du. We're very, very close. We need to have no 2. So what you do is we write this is x dx du over 2. So now, after our u substitution, our y equals x e to the power x squared dx. When I do the u substitution becomes, now x dx, remember, is du over 2, and integral of e to the power u times du over 2. Now I can take the constant outside. It is the integral of eu du. And we all know the integral of eu is eu. Half e to the power u. Now remember, when you're doing integrals, we always put a constant in the end. Now, remember, we started with the u substitution. We had to get back to the original problem, which was in x. So replace the u by x squared. So your final answer is e to the power x squared over 2 plus c. Okay. Now, we have learned how to find a general solution. We're going to talk about particular solutions. Now, remember, to obtain a specific value of a constant that is called a particular solution. That is, remember, we just had y equals plus c. So particular solution means finding that c. Proper definition is to obtain a specific value of the constant, which we call particular solution. What we do is we need the value of the function for a specific value of x. And the terminology we say this specific value is called an initial condition. Now remember this time we talked about y equals the beginning we talked about, which was it? Yes. Now, in the slide 6, we said y equals c e to the power negative 2x is the solution of this differential equation. Now, if I give different values to c, you will see the graph here for different constants. I get different solutions. Remember, it's an exponential solution. If you remember, y equals e to the power negative x is a graph which goes like this. I'm just making it, Okay, so this one is from your pre-calculus days, guys. Now here, if I put c to be 2, so what is going to happen? This graph is going to move up by 1 unit. So here it is this, c is 2, this is where your graph goes down. If your C is -1, you see the graph has kind of flipped from this graph. And then if you put C to be -2, so these are 4 different solution curves to our differential equation y prime plus 2y equals 0. Now what we're going to do is we're going to take a higher order differential equation. And this higher order differential equation is given as s double prime t equals -32. And we're given some initial conditions. So we want to solve this differential equation. And because of these 2 differential initial conditions, we will be looking at a particular solution. Okay, let's begin. First, we'll find, remember, the general solution. So we are given s double prime of t equals -32. We can write s double prime t, if you remember, d square s over dt square equals -32, which we can write this second differential as d dt of ds over dt equals -32. So now this is the one you would like to change it into a nicer form so that we can do our integrals. We can write this as differential of this ds over dt. Again, it's a differential of a differential, and we're writing it as an equivalent differential form, -32 dt. Okay, now remember, we want to get rid of these differentials because our solution is basically s. Remember, this s is our solution. So when I integrate the first time, what happens? Okay, so we get integral of d of ds over dt equals integral of -32 dt. So remember, this integral and d cancel out. We're left with ds over dt equals -32t plus c1. Okay. So let me write this again, because remember so here we will have to do 2 times differential integration. So, 2 times integrals so as to get to s. Okay, so let's see, this is ds over dt equals -32t plus c1, or I can write this as s prime of t equals -32t plus c1. Okay, continuing further, I can write the equivalent differential form as ds -32t plus c1 dt. So once again, we integrate, we get ds equals integral of -32t plus c1 dt. So doing the integrals, this becomes s of -32t squared over 2 plus c1 2 plus another constant, say c2. So my s, or I can write this as s of t, because s is a function of t here, -16t squared, okay, this is t, c1t plus c2. Now remember, this is the general solution of the differential equation given by s double prime of t equals 32, -32. Okay, remember, we are given initial conditions. So we want to find the particular solution. In other words, these two initial conditions will help us get C1s and C2s. Okay, so let's do that. So once again, let me write it down. The general solution of S double prime of t equals -32 is given by S of t, which equals -16t squared plus C1t plus C2. Now remember the two initial conditions we are given. And that is S of 0 is 80 and S prime of t is 64. Okay, so as we already know S of t, let's substitute t with 0. So when I apply S of 0 equals 8t, so what is S of 0? Using this equation, say star. So when I put this, initial condition in equation star here, so this becomes -16 times 0 plus C1 times 0 plus C2. So what do we get? 80 equals C2. Okay, but we are still left with C1. Okay, so let's write it down what we're getting. -16t squared. I do not know what is C1 here, but I definitely know C2, which is 8. Okay, to find C1, remember, while we were solving this differential equation, we found after our first integral that S prime of t equaled -32t plus C1. Okay, so take that. So S prime of t is -32t plus C1. Now we will apply this initial condition. S prime S prime was 0, not t here. Yeah, so S prime of 0 equals 64. So let's substitute it over here. 64 equals S prime of 0, and this part, which is -32 times 0 plus C1. So 64 equals C1. So our original problem, which was the general solution of this S double prime, was -16t squared plus C1t plus C2. So C1 is 64. So the particular solution, so remember the particular solution for this differential equation with these two initial conditions is given by -16t squared plus 64t plus 80. Well, as usual, when we do some examples, we need to do some practice. So here are some practice problems for you to do. And then in the next video, I will be doing the numerical approach, which is the Alice method, to do the finding a solution of a differential equation. Thank you.